Here we go. Okay, so we're now in chapter 6, the periodic table. Periodic table is the most important instrument any scientist can ever have. And we're going to go through it. You're going to learn how to read it. You're going to learn how to use it on an everyday basis. That's why I always ask you to make sure you get it out every time. I'm sorry? Yes, it's a bathroom shower curtain. It's kind of fun, isn't it? My daughter had one like those in college, which was fun. But anyway, so let's, I like starting my periodic table chapter off with this. It's a lot of fun. I hope you enjoy it.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, and lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, oxygen so you can breathe, and chlorine for your pretty teeth, neon to light up the sign, sodium for salty times, magnesium, aluminium, silicon, phosphorus, then sulfur, chlorine, and argon, potassium, and calcium so you'll grow strong, scandium, titanium, vanadium, and chromium, and manganese. This is the periodic table, noble gases stable, halogens and alkali reactive recipes. Period will see new outer shell will be electrons are added moving to the right. Iron is the 26th and cobalt nickel coins again. Copper, zinc, and gallium, germanium, and arsenic, selenium, and rhodium. Will krypton outside of your room, rubidium, and strontium, and yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silverware, then cadmium and indium, tin, antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56. And this is where the table splits, where lanthanides have just begun. Lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, chromium, erbium, thulium, terbium, lutetium. Hafnium, tantalum, tungsten, and we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, barium, and lead that is for your tummy, polonium, acetine, potassium, radar, and helium will last a little time, radium, then actinize at 89. This is the periodic table, noble gases stable, halogens and alkali reactive recipes. Period will see new outer shell will be electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, rhodium, nobelium, nobelium, lawrencium, mothercodium, rhodium, cerium, borium, cesium, mercurium, obsidium, ruthenium, copernicium, nihonium, barium, moscovium, limurium, tennessine, and organesson, and then we're done.
Wasn't that fun? That's a fun way of studying periodic tables. Okay, so obviously we haven't known about the periodic tables, all the elements, all this time. It started off a long time ago with, Democritus thinking that the atom was just a hard little shell, a little indivisible sphere. But then Dalton came along and he started working with things. When he started working with them, then they started really paying attention to elements. Okay? So pre-1700s, other one's over here. Not going to work. Too many gadgets. And then you have elements up to 1899. And then obviously here's all the elements we have now. And you can tell how old the slide is because look, we have some spaces left open. And these are all named now. But it kind of gives you some ideas. But most of these were discovered in the 19th and 20th century when technology became a little bit better and we could actually find more things. These are John Dalton's elements. He put he used these symbols. Just like we use, for uranium, it's U, which is still there. Iron, we use Fe, and he has an I for it. But these are what he used originally. We don't use it, obviously, anymore. Then comes Dmitri Mendeleev. Dmitri Mendeleev is the father of the modern periodic table. Now, he wasn't the first one to publish in periodic table, or he wasn't the first one to create a periodic table, but he was the first one to publish it. That's what made him the rock star of the periodic table. Okay? There are other guys, Meyer, who came up with one as well, but he published it and he used it with his students. He arranged this by atomic mass. He took all the elements. If you look over here, he took these numbers and he arranged them. They didn't have all the atomic numbers at the time, so they just used atomic mass to put these in some type of order. Now, the thing is, even though we know Mendeleev as being the creator of the periodic table for the most part, that's really not what his scientific awards were for. He did other things. He did some of the most important things by predicting elements that weren't there yet. And this is going to show that to you.
The periodic table is instantly recognizable. It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius. Up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitri Mendeleev, is a bona fide Science Hall of Famer. But what? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really. That had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum. Eka being Sanskrit for one. Nobody's found Eka aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time. Scandium, germanium, rhenium. The element he called ekamanganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitri predicted its existence, 30 years after he died. Dmitri died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitri Mendeleev, the architect of the periodic table, will be staring back.
Okay, so he's really known more for his predictive properties than he is for the periodic table itself, which is great, actually. So if you look at, here's some other predictive properties he had. There's the ecosilicon, and this is what germanium was as well. So it really, it kind of really set him into the record books of that, he understood the periodic table. Simple as that. And here's some other ones. All of these are the greens are the ones he actually predicted that actually came about. And all the properties were almost dead on what he said they were going to be, which is very kind of cool. Very cool. Okay, but then came along Henry Moseley. Henry Moseley was an English scientist who was the first one to come up with the idea of atomic number, but he assigned the atomic numbers to all the different elements. Okay, so he developed the concept of the atomic number. He uses X-ray diffraction setup, but he determined the atomic number for all the different elements, he and his crew. Okay, so here's my atomic numbers up here. These blue numbers up here, and the red are obviously atomic masses. He arranged the elements in order of increasing atomic number. And that's what our periodic table is of today. It's the same as it was back then. So he had to move a few around. So if you look at tellurium and iodine, they were actually flipped on Mendeleev's periodic table. And so was cobalt and nickel. These two are flipped as well. So it really didn't change the periodic table all that much. But our periodic table now, the modern periodic table, is arranged by atomic number. And what they saw was this. When you arrange the elements in order of increasing atomic number, you see a periodic trend. Every so many elements, the same properties show up again. So they didn't look at the transitions back then. But every 1, 2, 3, 4, 5, 6, 7, 8, you go back and you have the same properties. The elements in this first column are very volatile. They are all gray soft metals. But you put them with water and they either blow up, they fizz, they're very, very reactive. So every eighth element, he came back to this reactive gray soft metal. Then, again, this column here has a bunch of very highly reactive nonmetals. So he kept seeing this trend of every so many elements, you saw the same properties. That's called the periodic law. You need to know this, okay? You need to know the periodic law. So when you arrange the elements in order of increasing atomic number, their physical and chemical properties show a periodic pattern. It means it's a cyclic type of pattern. So I know every time I get back to group 1, here's what these elements are going to look like. Here's what they're going to be like. Okay? That is the periodic law. And that helps us predict elements and what they're going to do. Not predict elements, predict the properties. I know if I take alkali metals and put them with halogens, I'm going to get a reaction. I'm going to get something called a salt. And you're going to learn to look at that and be able to read the periodic table. Okay? Glenn Seaborg was the nice guy. He is a really nice man. He actually came out to Fernald at one point in time. Fernald, down the road. Fernald was a really cool place. I mean, highly radioactive and things like that. But the amount of science that was at that facility down the road, gosh, Trenton, I wish I could show you what it was. Okay? Right? Okay? They had huge machines, all kinds of really cool machines, mass specs out there, just the equipment was outstanding. I worked out there for a few years as an educational specialist, and we got to learn all the environmental laws, and got the right tests for the lawyers and for the physicists. They had to know the environmental laws. If they didn't, obviously they should not be working at a Superfund site. And because everything was really, really, dusty and radioactive, and at least in the hot areas and things like that. But Glenn Seaborg actually went out there and spent some time at Fernald, and I worked with some people who actually got the meeting and stuff. They say it was just really, really nice. But he's responsible for the identification of more than 100 radioisotopes of the actinide series. Okay, so he figured out a lot of the isotopes for these elements down here. So cool. And if you go to Albuquerque, New Mexico, you can actually go and see the instruments in which he worked with. I've got a picture of one back there. Once I take the holiday stuff down, I'll put the picture back up. It's so cool. So you get to see his electroscope he worked with, and it's an atomic history museum. So it's got a replica of the Fat Boy bomb that was dropped on Nagasaki, and how they came about with it and stuff like that. Cool, cool, cool. Okay, so here's our periodic table of the elements. We all know this, right? Your symbols, your names, your masses, things like that. Here's one in German. Now notice the symbols are all the same, but it's the words that are different. Instead of hydrogen, they have, I think it's Wasserkopf. It's like the water maker. Wasser is water in German. And so H2O makes water. So the name is Wasserstoff. Zinc, I can't read some of these because they're too blurry. But the names are different, but the symbols are the same. That's what you have to understand. When you do these symbols, you need to make sure you know them and are writing them correctly. If not, it doesn't make sense. Here's one that's in Spanish. Again, the symbols are all the same. The names are different. This is Greek. Again, symbols are all the same, but the words are in Greek. And then Japanese, okay, or Chinese. I think it's Chinese. I'm sorry, I looked up a Chinese one. And so, again, the symbols are the same, but the words at the bottom. Sean, no. I need you to sit in that place. Okay? So, what are elements? Elements are pure substances. Elements are, I think I changed it. Elements are substances that cannot be broken down any further. So if I take the element lead, and I try to break it down, I can't break it down any further. It doesn't change. Lead is lead. It's the smallest part. Elements make up matter. Atoms make up elements. Okay? Okay with this? Okay. So they're the building blocks of matter. And we know the symbols represent these. Some of you guys are still writing the symbols lowercase. Someone wrote a lowercase e and a lowercase h, lowercase e for helium. You cannot do that. You have to make a capital first letter, lowercase second letter, if there is a second letter. If you don't, it will be wrong. I'm just telling you right now. I will have to mark those answers wrong. Even though if everything else is correct, it has to be wrong. We write them a certain way for a certain reason. Sometimes we have Latin names. We talked about this early on. Iron is ferrum, silver is argentum, gold is aurum. We kept some of the Latin names, and we still use them. I'm not quite sure why they did change them, but we still keep them. Okay, now groups and periods. Let me give you a new blank periodic table. And that way you can write some of this stuff down on it to keep it nice and neat if you'd like. There are some colored pencils in the back if you want to color code your periodic table as you do this. Does you all have one over there? 2, 4, 4. Do you guys need to come back there? Okay. So this. And you always pass it over this way if ever you have extra. There you go. Just 1, 2, 3, 4, 5. Okay. Sorry. So, groups and periods. Elements are arranged on the periodic table according to their physical and chemical properties. They have similarities, some of them do. Groups contain elements with similar properties in vertical columns. So if you look over here, the columns that go up and down the periodic table, these are our groups. They're also called families. So they're groups or families. And they have similar properties. Just like when some of you guys walk in, I know immediately what your last name is going to be because you look so much like your siblings. Okay? And poor Miss Emily walked in, I'm like, oh my God, you got to be Tony. And I'm like, okay, I know exactly who you are because you have similar family properties. Correct? So that's why we call these guys groups or families. Periods are the rows. There is nothing similar about the elements in a row except for what energy level they're in. Because our periods, or the rows, tell us our energy levels, right? Yes? Good? Okie doke. So on your paper, make sure you know that the groups come down and the periods go across. How many groups do we have on the periodic table? 18. There are 18 groups on the periodic table. Now, back in the day, when I first started teaching, we actually used to call 1A, 2A. Groups 1 and Group 2 is 1A and 2A. And we skipped the transitions. And Group 13 was 3A, 4A, 5, like this. That's the way it's written because the S groups, the S blocks here, and the P blocks are our representative elements. They represent all the different elements possible on the periodic table. So Group 1, Group 2, and 13 through 18 are our representative elements. On a test, I may say something to you like, hey, which one of these is a representative element? So you have to know where they are. Okay? But now we just do 1 through 18. So I just show this to you because sometimes on tests, like state or ACT or some other type of standardized test, they may still put these B's in there, the A's and the B's. I don't want you being confused. So the A's are your representatives. Okay, but then the periodic table is actually split into two big groups. You have the stair-step line going down, cutting the periodic table into two pieces. Trent, I need you sitting up, please. Okay, so you have the left side of the periodic table and the right side. What's on the left side? Metals. Metals are on the left side of the periodic table, but 88% of the periodic table are metals. Okay? All these guys from the stair-step line over are metals. And everything to the right of the line is non-metals, okay? Non-metals. Now, they got this whole metalloid thing, and some of you guys wrote to me about the metalloids. The metalloids is kind of like brackish water to me. You know, sometimes they act like metals, sometimes they act like non-metals. But the problem is, they're not a metal, or a metalloid is just, in my term, a made-up name for something that lies along that line. I won't ever ask you that on a test. I will never ask you if something's a metalloid. I'll ask you if it's a metal or a non-metal. That's all we go by. Okay? So if it's to the left of the stair-step line, it's a metal. To the right is a non-metal. Plain and simple as that. Yes, sir?
So there's green metalloids?
They are the metalloids. But they're also, germanium's really a metal. But germanium does not conduct heat and electricity as well as most metals do. So they call it a metalloid because it's not a really great conductor of heat and electricity. Silicon is a non-metal, but it tends to conduct electricity in semiconductors. It doesn't act like it should, but it's really a non-metal. So it's a metal or a non-metal. We're not going to do the brackish water metalloids. Okay? This gets old. Once they took aluminum out, it drove me crazy. Aluminum used to be a metalloid. In my book, aluminum should be a metalloid. So once they got rid of aluminum, it just kind of ruined the whole idea of metalloids. I mean, it's like Pluto not being a planet. Who thought that was a good idea? You know? There went astrophysics in my book. You know, sorry. Let's get into it. So metals are typically shiny and ductile. Do you guys know what ductile means? They can be pulled into wires. Excellent. Good job, Jackson. They can be pulled into wires. What's the other term when you can hammer them into flat sheets? Malleable. Malleable means you can actually shape metals. Metals, you melt them, you can shape them. They bend easily. They're also great conductors of heat and electricity. That's why all of our wires are made of metal, for the most part. That's why we use metal pans to heat our food. I don't go and get, piece of wood of some sort, try to heat my food. It probably catch on fire and stuff, right? Okay? Non-metals are dull, they're brittle, and they are not good conductors. They're actually insulators. They tend to insulate away from heat. And of course, metalloids fall in that middle section there somewhere. So far, so good? Yes? It's not difficult, is it? Trent, I need you to go stand up, please. Okay? Your eyes have got to stay open. Take your notebook with you so you can take notes and stuff, please. Okay? Let me know when I can. Okay? So, you can compare metals and non-metals and metalloids, but the thing is, metals are used in coins and jewelry and tableware and things like that, where sulfur, which is a non-metal, is powdery. You can use it in gunpowder. We use it for in drugs and things like that in our soil, and it's just different. Metals just fall under a different class of non-metals. But most of our periodic table is metal. Okay. Now, names of some representative elements. On your periodic table, I want you to do this. I want you to write these groups down. You can use some colored pencils on the back if you'd like. I'll give you a few minutes to do this. Oops.